So here's my current U-loop configuration up into the rafters, and it's very limited on what it can do. It's only 1/4 of a watt rated, and it was this idea of having the connections. This has been outdoors, which is not really designed for, but having these SMA plugs that you can plug in and out, that gave me the idea to make a configurable antenna. So here I have got 5 meters of RG213, which is thick and hard to work with. And as I mentioned in the blog article, you need to use these special plugs that have a larger opening. Quite difficult to solder. Little portable blowtorch comes in very handy. And 5 meters down the road, of course, there's an identical connection on the other end. So it weighs a ton. And we can try multiple configurations. We can do a single loop, we can do a double loop, we can wire the inners and outers differently. That's the main loop. Well, this is the coupling loop. The coupling loop is 1/5 of the diameter. Not diameter, circumference. Mag loops always talk of circumference. This is tatty, it's just a test. So you can see that I'm only wiring to the outers at the moment, and we can play with that configuration. It's just simply an SO239 socket. At the moment, not connected or mounted on anything, but we can just plug our feed from this one, from the U-loop. We can take that feed and plug it straight into here. I can switch antennas easily, and I can change the configuration at no more cost than a new socket and a bit of wire. And that's really what I'm interested in with this, is making it as configurable as possible. So we can try double loops, we can try delta loops, we can try squares. I'm going to hang it on the garden fence. There's the garden fence, which has got my long wire running along it. Ignore the neighbour's TV aerial. But I can hang my new loop on there and experiment with it. And we'll see where it goes. So, more when I've done a bit more testing and building, and hopefully you'll enjoy it. Okay, so here's an overview of how I think this is going to work. I'm going to have a main resonant loop made of RG213 coax, and we're going to start this off at 5 meters as a sort of maximum. Firstly, because I bought 5 meters of cable, and secondly, because I can shorten it, but I can't make it longer. So we'll do some tests at 5 meters, right through the nano VNA, see what the results are like, and then we'll adjust it accordingly by just making further calculations using online calculators. This is going to be tuned by a variable capacitor, an air dielectric one, an old valve radio one with 2 gangs on. 2 gangs are going to be in parallel. They're 100 picofarads each. This is what my calculations tell me. The inners are not currently used. I'm aware you can fold the inner onto the outer and vice versa to double the length of it, so that's going to be another thing. They're going to be in a plastic enclosure with SO239 sockets, PL259 plugs, and I'll be able to hot wire them across on the box, as you'll see. That's going to be controlled by a stepper motor. Stepper motor is going to have a controller, a ULN2003 controller. This allows it to have 8 phases of operation, and it takes care of all of that for you. You don't need to worry about it. So for every step it'll jump through a little sequence of the 4 phases, and the phases overlap. So you get A and B, B and C, C and D, D and A is the full sequence. So you get a total of eight steps, but it actually does it all in one go, and that gives it quite a good torque. The other nice thing about this is that the stepper motor has got a built-in 60-foot-1 reduction gear. So we can actually end up with about 260 steps to move 180 degrees, which works out about 0.7 of a degree per step. Is that enough? No idea. We'll find out when we try it. So the stepper motor is going to be controlled by an Arduino Uno initially, This gets replaced with a nano later on. And rather than use up and down buttons, I decided to use a digital encoder for two reasons. Firstly, never used one, so is it any good? Will it do the job? And I like the amount of control it would get. I first encountered a digital encoder in 1980 when I worked for Raycall Communications, and the tuner was done by an optical digital encoder. And it was amazing because you could move it slowly and get the steps, or you could spin it and it would spin literally from 0 to 30 megahertz with a really good spin. Quite a good source of amusement in those days. Unfortunately, these ones use mechanical contacts which have a habit of bouncing, so not quite as good quality. So to overcome some of that, I've used the push switch so that when you press the switch in, it changes the step count from 1 up to 5 or maybe 10. So if you want to travel a long distance when you change wavebands, you can push the button, spin it, not too fast, but you can spin it and move faster. And then you can click it off to get the fine tuning when you get there. That's my thought. The pickup loop is a metre of RG58. Same rule again, that's the maximum length. It's a fifth of the coupling, a fifth of the main resonant loop size. You can go down to a tenth, so I can cut some off. I can also replace it. RG58 is so cheap, I can make multiple versions. Because there's no actual physical connection other than some insulating tape or whatever, we can change this quite easily. So this is a completely experimental development system. It's not going to be a finished product. It's a good starting point. And we'll see what happens. I didn't want to rip up a £300 mag loop to experiment with this. But this cost me, 30 quid in bits. Who cares? All it's going to cost me if I cut too much off is another piece of RG213 or another piece of RG58. As regards the electronics, they cost peanuts. The stepper motor is like £10, £12. The digital encoder, I think it was a £5. None of this stuff costs a ridiculous amount of money. So I think it's a good place to start experimenting. That is the key. So let's see how I get on. Okay, so we've got a few simple parts to this. We've got the ULN2003 motor controller, the ULN2003 motor, a bracket which I had to drill extra holes into because this motor has an offset drive shaft, which you can see there. So it's approximately in the centre. I've only done it by eye. And then we have our variable capacitor, which has got two gangs, which I can configure this in different ways. The box is going to form the base of the main loop. So the loop will go round, it's going to be 15 foot long, so the loop will return. Because these sockets are isolated by this plastic case, I can configure them in different ways. So I can connect the inner on one to the outer on the other to double the length of the loop. That's something I want to experiment with. Also try using the inner instead of the outer. And the same is true with the capacitors. So I may end up with some switches on here yet, or I may just dummy up the connections. So it's just a standard component box that you can pick up anywhere. I bought it for no particular reason. I didn't buy it for this. The capacitors are just glued to it with EVA adhesive. Again, because it's plastic, everything's isolated, nothing's going to cause any problems, even if you put quite a decent power into it. The little ULN controller is a 4-phase stepper motor, which has 8 states, and they're controlled in software. And for one step, it goes through all 8 states. It's then geared down at 64 to 1 in the motor. This is really useful because it means we can do really small steps, and we can also vary the speed in software that it makes the steps at, as well as the step sizes. So there's a bit of stiffness in the system and not everything lines up correctly yet, but this coupling will let you use it, as you'll see in a minute, with quite an offset. It's certainly not lined up. But once I put some extra washers under here, I'll get the height better and it'll be more free flowing. So what I'm going to do now, I'm going to initialise the software by uploading it to the Arduino. And you'll see it do a little cycle. First thing we had to do was calculate what 50% of a turn was. That's easy. When you get the software, it tells you how much one full turn is. So you divide it by half. And it turns out this capacitor goes a little bit further than 180 degrees. So you just tweak the figure until you get a nice clean run. So I'm uploading the software now. I've been playing around with the software for a couple of days. And you'll see it rotate anti-clockwise, depending which end you're looking at it from. Get to the end, and then come back again. There we go. And now you see the sequence has stopped. Now we can fine tune it. It's a little bit reluctant to start sometimes. And I need to get the timing better on this actuator. Now you can see on the left hand side the LEDs are running a sequence. Every time I do click it once, it does a full sequence. If I click the button, it now goes 10 steps at a time. So we can do our manual initial tune on receive really quickly. And when we've got roughly where we want, we can put the SWR meter on. And hopefully, I'm going to have to strip this and spray some WD-40 on it. I've literally not done much with these capacitors since I got them. They've been sat in a guy's shed for years. He literally has boxes full of this stuff and they've never been connected to anything. They've never been soldered, ever. So it wants a little overhauling to run smoothly, but I think you get the idea. You can see it is rotating. Sometimes you just need to get the timing right in the software as well. But it is going to work one way or another. Also, I'm only powering it from a USB lead, which is limited to 500 milliamps. This motor does like more power, so eventually there'll be a proper DC jack going in here. And then I'll be able to power it up properly. I have noticed a substantial increase in performance when you do that. It's a nice little unit, and I'm also going to provide a shutdown that will close the capacitor just to keep dust off it. I also note there's a bent thing there through it being thrown in a drawer. So that's probably the cause of the shorting out. When I bought it, the vanes were offset and were not symmetrical at all. And there's a screw on the end. You just loosen the outer screw and gently move the inner screw a little bit. So yeah, a little bit of maintenance. To buy these capacitors online, you can pay £40–50 for them. I got two for like 15 quid. So I'm very happy about that. And I can refurbish them and use them as I need. So it's going to be an interesting project. There'll be a lot of playing around to get this software to work the way I want it to. I'm on the third evolution of it already. The other nice thing about it is there's no drivers needed. It just runs from a program. The bits of the program I'll show you later. There's only a few lines of program that are actually to do with the motor. The rest of it is all for my controls, so that's going to be interesting. So here's the head unit in inverted commas. The stepper motor. This is now realigned to work a bit better. The circuit board is now done on a prototype board and all soldered up and tested. The blue and white wires here are for the DC input, and that's going to go back to a little wall wart plug adapter. I'm going to send 9 volts into the V-in socket, and 5 volts is going to come out of that and power the motor. It will supply 900 milliamps maximum, which should be enough, and it'll also power the Arduino Uno. Now, I know it's Easter, and this was completely unintentional, but I've made a crucifix. Sorry, didn't mean to offend anyone with that. So we've got the full 5 meters of RG213 around the outside, and we've got this ramshackle loop at the bottom. I'm using the full capacitance. I've got the two gangs connected together, and the earth on the other side, and they're connected in the box to the outer on these PL259 SO239s. It's not going to be suitable for outdoor use, so it'll be coming in at night when I finish playing with it. So all I've got to do now is loop some cables through the window and stand it up against the house and see what happens. Sorry for the shaky video. There's no realistic way of doing this with a handheld camera. So let's plug it in and see what happens. So, does it work? And what constitutes working? So we've hooked up the Nano VNA to it, and I'm scanning from 1.5 megahertz to 30 megahertz. We're looking at the SWR, and clearly it's pretty atrocious. If I zoom in on this bit, there's a bit around 10 megahertz where it dips. But what I want you to look at is there's another thing that appears to the left of that. If I just tune it slightly, we can see that as the capacitance changes, the dip moves to the left. Exactly what we'd expect. So rather than sit there winding it backwards and forwards, if I reset the unit, it'll do a full skim. And I'll do it twice. So it's going to go all the way open and then all the way closed. So we can certainly tune it over a range. For some reason at maximum capacitance it chooses to disappear. Now, because of this strange characteristic, I've double checked all my connections this morning, and I think they're right. But I've clearly got a lot more work to do on this before it's any use. So it's an interesting concept, and I'm quite interested to see how it ends up. But it's not as yet a practical mag loop. So I'm going to have a play with it and come back and report further down the line. I hope you'll agree it's an interesting project, and we'll see what we can do with it. Maybe I need to tweak some values. I did do multiple calculations for different bands, so I can compare these results to those bands and see what I can do with it. So, in part 2 I'll be explaining the code for the controller. So, see you shortly. Okay, so this is the code for my mag loop tuning motor. I started off with the code for the ULN 2003 interface board. This sets up the variables for the connections to the pins. These are for the final version that I did for the Nano, so the pin numbers have changed from the original. But it only uses 4 pins. We set the maximum motor speed. Well, we actually set it's not the maximum, it's the motor speed. Higher is slower because it's used in a delay loop, which we'll see in a little while. We need to set up this integer array. This predefines the patterns for the steps for the motor, and they're done bitwise binary, if you understand that. So you can see on that one, the 8-bit is set. On this one, the 8 and 4 bits are set. On that one, the 4-bit is set. On that one, the 4 and 2 bits are set. On that one, the 2-bit is set. On that one, the 2 and 1 bits are set. On that one, the 1-bit is set. And on that, it's the 1-bit and 8-bit. So that basically represents A and D, A and B, B and C, C and D, D. Whew. That's the basic idea. For the digital encoder, I need to store the states of the A and B inputs. And I did a lot of messing around with this because It's very easy to just increment a value up or down, but to make the motor obey it is slightly different. The reason being that when it drives the motor, it causes a delay in the processing. So I had to modify this code from the sample code I was using. So I needed to monitor the current state of the B input as well. This is the step size, which at the moment is only working on 1. For the same reason of delays, when you change it over, I'll refine this code further down the line, not a problem. This was originally counts per revolution. It was 512. I find it needs 265 to fully move the capacitor from end to end. And I need it to hit the end stop at both ends to make the calibration work properly. Usual LED pin. I just want to show when it's getting an input. When we start remote controlling it and wanting to do stuff over longer distances, this is going to become an issue. So these are the pins for the digital encoder, the A input, the B input, and the switch. And that is the current position. Not too bad. So initially, we set up our digital encoder, and we'll program our pin for the switch, the A input and the B input, and I used the ground terminal, or at least a common terminal, and grounded it. That way I can use internal pull-up resistors in the Arduino. It does mean that the inputs are high all the time and they go low as you switch. It's not a problem. Something I could experiment with again. And the same for the motor out. The motor pins, 1, 2, 3, 4, program all those as outputs, set up our serial port for monitoring. And the first thing it hits then is init motor. I love the way it says that. And there's init motor. So all init motor does counts from 0 to the counts per half rev. Increments 1 at a time, all the way up. Then just the same thing but backwards. Starts off at counts per half rev. And I've let it go faster. I've let it do 5 pulses at a time. And that's it. So that will then return back up to our loop. Do a quick grab of the current state of A input, and then we're ready to go. So the main program loop looks at the current state of A and B. If the state of A is not equal to what it was previously, you've turned the pot, the controller, the digital encoder, sorry, not pot. It's not a potentiometer. If the state of B is the same as A, then it needs to go clockwise. If it's not, it needs to go anti-clockwise. Now my position up and down is a bit random, but it's not important to the operation of it because it's this clockwise and anti-clockwise that are going to do the work. I am limiting the value of pause, so if it tries to go negative, it'll limit it to 0. If it tries to go higher than the counts per half rev, I'll set it to that. That's just really for debugging purposes, it doesn't really do anything. And then we pass the current state of A into the previous state of A, so that the next time round it knows what it is. And that's it really. I've made a thing for the shutdown, and then the clockwise and anti-clockwise just do 8 steps. And all it does is it grabs the output using set output, and this does a bitwise lookup and sends each of the 4 bitwises, one after the other, to the motor. Appears to do it twice as well. But that's all the standard code that came with the motor. There's no driver. You just pulse your outputs and it does it. Here's the motor speed, and this has a function I've not seen before. Delay microseconds, because normally it delays in milliseconds. Now this motor can obviously go quite fast. And I did manage to find a definition for that. For some reason it's not doing its definitions today. But it is an internal Arduino function. and it just allows you to set time in microseconds rather than milliseconds. So that is the code. There's nothing to see really. I will continue to update this. I'll post it as is for now. And then if you just want to replicate it, I've commented all the code so you know what's going on. The initialization. When it does this and it hits the end stop, people say, oh, it's going to draw an excess current because you're slamming it against a brick wall. Actually, it's a stepper motor. It doesn't care because it only receives a pulse. It hasn't got constant current going to it like a DC motor. So it just gets a pulse and a pulse and a pulse and a pulse. If the motor moves, it moves. If it doesn't, it doesn't. You can quite happily stall it. And so long as you're not sending input to it for hour after hour after hour, it won't bother it. So you can synchronize it simply by taking it fully anti-clockwise, fully clockwise, and you should be back at 0 degrees. So I can't see a problem with that. The only problem I have found is that because I'm running the Arduino in the middle of a mag loop, it's picking up the signals from it. And every 16 megahertz, I'm getting activity. Allow me to show you. So here we are in Arduino. It's hooked up to my SDR Play RSPDX. And here's a suspicious looking signal. And if I unplug the Arduino, it disappears. So if I plug it in, you can now see the motor working. And when it gets back to the end stop, the frequency changes back again. So this is something I'm going to have to look at and potentially mount the Arduino in a metal box. But there's other considerations as well, because at the moment the digital encoder is sat right next to the Arduino. So unless it's right outside my window, I can't operate it. So there's a couple of possibilities. One is I need to attach some longer wires to the digital encoder. I'm not really convinced that's the best idea. What I may do is transfer the code to an ESP32 or 8266 that's got Wi-Fi, and use Wi-Fi or Bluetooth to control it. So, as with many things, it's work in progress. We'll have to see how it goes. But what I did find is that on 15 meters, going to be nobody on it now that I want to show you. So that's on my long wire at the moment. Sorry, the loop would have picked up that interference much better. But if we go to antenna B, which is the mag loop, there's a definite increase in signal level. Not so on most of the other bands though. So that's better on the long wire on 20. 40. Much better on the long wire. So the tuning leaves a lot to be desired, and I do feel it's the case that I'm going to have to shorten the main loop. I'm going to run some calculations on that and see what happens. So I hope you enjoyed the video. I've moved to some suggestions if you've built one of these yourself and tried different types of motor drive. I hope it's going to work out. We're in the spring now, it's dry, I can hop in and out of the house at random and make as many modifications as I like. So have you built a multiband mag loop? And if so, have you done a motor drive version? Because I'm really interested. I know there are some compact ones that use a double loop. I didn't really want to do that, because I saw a lot of the guys in the States use really big ones. And although I don't have a really big garden, I thought it'd be quite ideal. So, talk to you soon, 73s, and please subscribe and please like the video. Bye for now.